Ladies and gentlemen, welcome to track number 3, Next Generation World Builders, powered by Tech Plus IP Advisory. Here we will explore how science and engineering shape the future of society across borders, disciplines, and even planets. Now, firstly, I would like you to scan this and provide us with your feedback for these 2 days we have been having the keynotes and sessions. Of course, later I will give you for the track also the QR code. We will begin with Nerma Čaluk, structural engineer at Skidmore, Owings and Merrill. In her talk, Next Gen World Builders, Engineering a Life Across Two Worlds, Nerma will share her complex journey from Bosnia and Herzegovina to working on structural projects across the United States, including pioneering research in lunar infrastructure. Her story highlights how strong foundations, adaptability, and curiosity can empower the next generation of engineers and innovators. Please welcome Mrs. Čaluk.
Dobar dan. Da radi. Da, tu sam ja. Okay. Dobar dan svima. Velika mi je čast biti ovdje na Future Leaders Summit i govoriti pred ovom našom bosanskom zajednicom koja aktivno gradi mostove između mladih lidera ekonomskog razvoja i globalnog znanja sa ciljem da unaprijedimo Bosnu i Hercegovinu. Željela bih prvo zahvaliti Edemu Čustoviću na gostoprimstvu i na svojoj organizaciji i čestitati na 10. godišnjici. I također bih željela zahvaliti BiH Futures Foundation što su me pozvali ovdje, omogućili da budem i da prezentujem svoj put, share my experience sa našom bosanskom zajednicom. Iako je danas glavna tema moje prezentacije karijera i građevinstvo, željela bih, veoma mi je važno naglasiti da do ovog puta ne bi mogla doći sama, do ovog mjesta ne bi mogla doći sama i bez roditelja, bez sestre, bez porodice, prijatelja i svih onih koji su me nosili kroz tenis, kroz školu i sve odlike koje sam donosila kasnije, moj put bi izgledao skroz drugačije. I oni su me naučili da disciplina nije uvijek bila pregovaračka, naučili su me da je upornosti koja me gurala i možda kada bi drugi odustali i također saosjećanje koje je davalo tu toplinu čak i kroz lekcije. Mi u školi učimo da su temelji ti koji nosi sav teret, svako opterećenje, svaku promjenu i da je to najvažniji sistem u izgradnji i ja mislim da je ova naša bosanska zajednica i moji roditelji i svi prijatelji porodica razlog zašto je sve to tu i zašto sve stoji i razlog zašto sam mogla da sve ostalo gradi. Kao dijete uvijek sam bila hiperaktivna, voljela sam tenis, sport, dubite na glavi, ali sam također voljela i knjige i čitati matematiku, fiziku, crtanje i odrastajući u Bosni nekako nisam uvijek pripadala u jedan kalup. Na jednoj strani sam imala takmičarski sport, tenis, a na drugoj strani sam voljela rješavati zadatke iz matematike, fizike i te neke tehničke stvari. U tom periodu nisam znala da je građevina bila pravi smjer, ali me uvijek nekako prirodno privlačila, vjerovatno zbog porodičnog okruženja i sklonosti za tim tehničkim stvarima. I gledanje u zvijezde nije baš bio najpraktičniji smjer što se tiče smjera u tom periodu života i zato sam se fokusirala na tenis i te praktične inženjerske smjerove koje su me kasnije doveli do Sjedinjenih Američkih Država. So going to the coming to the US was interesting and felt natural. So going to the US felt natural, and the language clicked with me. The language didn't overwhelm me. The culture was just kind of normal, and I learned it from the CSI Miami, so it was pretty interesting, and everything went kind of flowing there. But I did bring a lot of stuff from Bosnia. I brought the perseverance, I brought the compassion and the passion for work that I could share with the others around me, and also get this Bosnian community spirit back to the Americans as well. My teammates have taught me that social life. My teammates did teach me that my social life in another country. Then we had these 7 a.m. practices, 5 a.m. punishment runs, team losses that felt sometimes like personal tragedies that kind of bonded us together. And all of my teammates were actually from different parts of the world, and I think we only had one American on the team. My coach was in Serbia, so it was pretty interesting and fun team to work with. But Also, there was engineering. So during my studies at the university for my bachelor's, I was the only civil engineering student within my whole team, which meant that I had to do statics homework on a Friday night when everybody else was going to go out. I was doing differential equations on a plane when we were going to tournaments, or I was running from the classroom to the locker room, from the locker room to the classroom actually right after practices to catch my classes while everybody else was off to take a nap. But I loved it. I loved the challenge of it. It was very interesting, and it was just like kind of pushing me forward. I wanted to push the boundaries of that. So during that time, I did the math that felt very natural. I did a lot of like structural engineering and the mechanics of materials that pushed my boundaries in knowledge. And also, I have bonded with my small engineering group that they have drawn everywhere where they could and tried to explain how things worked. And we have bonded over a common philosophy is if we needed to write an essay that is more than one paragraph long, it was unreasonable. We just did not like writing. I think that's a common thing amongst the engineers. But we kind of managed there. And during this time, I finally found out, like, I started actually exploring how to have these identities between the two worlds, between the classroom and also the tennis courts, between the Balkans and the Americans, and also between the discipline of tennis and logic of engineering. So engineering was kind of my passion in that sense, and I continued it within FIU, where I was offered a full scholarship for my master's degree with thesis, where I focused on implementation of ultra-high performance concrete, which is very durable and more strong than like the regular concrete that we use. And we tried to implement it into accelerated bridge construction methods that is a program within the US. So the whole idea is to use this UHPC material to build prefabricated concrete columns. The shells, actually only the shell columns that are going to be prefabricated off-site, brought onto the on-site. And the idea is to reduce the construction time, have less impact to the traffic, reduce the long-term cost, and also provide for better structural stability and also the whole durability of the whole system. And during that time, I realized that the theory wasn't the thing that actually excited me, it was the lab. I had to cast concrete, I had to tie rebar, I had to, like my grandfather once did actually, I had to cast these full-scale specimens, put them on a testing lab, watch them being crushed, hear them being crumpled, get all this interesting data, push the boundaries of it, this like a bridge engineering, and it was so exciting to me, and it had a lot of challenges, but we published so many good papers, and I learned a lot about the research, and I kind of wanted to continue it. So my parents have realized that, and my mom just mentioned at one point, why don't you do a PhD? Imagine just being a Dr. Čaluk. And we already have a couple of doctors in our family, so I'm like, might as well keep the tradition alive. So I proceeded to start looking into research applications and seeing how I can actually do my PhD and where would I do it. But then COVID happened. A lot of things were uncertain, like for everybody else, and I didn't know what to do exactly at that moment, but there was a sign. Even though I did get into Georgia Tech, I have decided actually to stay at FIU because a person from NASA Kennedy Space Center has reached out to my advisor asking for a PhD student to jump on a project about lunar habitats. It's like building on the moon, and for me that was like, I was over the moon, literally. So it was very exciting and challenging, and I couldn't believe that opportunity, and I told it to my parents. I'm like, look, this happened. This guy wants me to work on lunar habitats, to stay here, get my degree, and get my PhD within this topic. And they're like, you can do it, but you cannot go to the site. You cannot go to the moon. I'm like, it's fine. We're not going there. That's not how the life works. But yeah, so I proceeded to do that, and I worked with Robert Mueller, which was my committee member from Kennedy Space Center, and he was very interesting, and his team was very interesting because they talked about this like you're going to a grocery shop. They talked about these materials like it's a normal thing. It's like you need to build this stuff, the lunar habitat out of this, you have the meteorite impacts, you have the moonquakes, you have the radiation, you have to design for this human life, for this persistence. And for me, it was just overwhelming and was like super cool to work on. So I proceeded with that. And so I started looking at a lot of publications, a lot of research, what has been done before since the Apollo era, and it was overwhelming, but I did manage to kind of focus on the structural analysis, identify the structural systems, identify what type of kind of constructability methods we're going to use, because humans will not actually build that. We're going to use robotic systems, so that structure needs to be designed to be built by robots. So we had to design for different loading criteria, like meteorite impacts, different type of vacuums, a pressurized environment, and so on and so forth, and also to have this human habitability aspect as well. So that's where kind of my research era started. The space research era started. But then towards the end of my PhD, even though everything was great and exciting, and I kind of bonded with my robotics group, I have realized that I wanted to do kind of leave that extreme environment research on the side and actually focus on a different type of rigor. A rigor where wherever I see I can actually design a structure, go onto the site, see the structure without my parents actually getting mad at me, and actually like go onto the site and do the inspections. So I kind of want to shift from that research and go into the practical world. But so that decision was actually made very easily because SOM has offered me a position to work with them in San Francisco. And I took it. And it was very easy because they're one of the most renowned architectural companies that have internal architects and engineers on the same company. And they are pushing innovations, pushing the boundaries of innovation, of engineering or architecture, sometimes out of just ambition because they want to, sometimes out of the necessity where the site is. For example, they have the Willis Tower and John Hancock Tower in Chicago, where they have completely redefined how we define structural systems and also how we design high-rises today. For example, in Jeddah, the Hajj terminal was designed specifically with these long-span tensile structures to provide for a very welcoming and publicly responsive kind of open space for the prayers or for the people, for the local people. We have the Genmao Tower that is located in Asia that kind of pushed the boundaries, like set new benchmarks for design using local materials and also construction methods that are very innovative and very different. And also we have the Burj Khalifa. They did the whole tower, and it was very interesting to hear them talk. I heard tons of internal presentation about it and how the whole thing was designed and put together. But it was designed so well based on the governing load, the wind loads, that it didn't need any additional damping. Like it did not need any additional stabilizing effects. The shape was specifically designed for that type of wind load, which was very effective and was tested through a lot of with the wind tunnel testing as well. So all that engineering and kind of stepping into that structural innovation, the new type of environment for structural engineers was very exciting. And I was a little overwhelmed because there was decades of engineering that has set this stage for me, for precedents for me, that I can build upon and test the boundaries of the future of civil structural engineering. So I'm going to run through some of the projects that I have been working on for past couple years that I have been working there, and hopefully they're a little bit interesting. So the first project that I worked on was Infinite 131, which is located in San Francisco in Bay Area, actually close where I work there. The city is in the background, all the way there in the background, the actual city, but this is in the Bay Area. It's a massive research and development project that is located in one of the highest seismic regions in the country and probably the world as well. So this specific system needed to house a lot of research amenities and a lot of different loads that are specific for the research facilities, and needed to have these open spanned floors, while also having the core systems that are intended to house a lot of amenities, different type of loading criteria, and also have the lateral systems, the systems that needed to resist the seismic ground motions. And the actual interesting thing about this is it was my first project, so I started to learn how different entities communicate, how we communicate with the clients, how we communicate with the architectural program, and how we actually design for an efficient structure to resist the extreme seismic forces within the region. So as I mentioned before, each of these buildings that are within the whole site plan required to have open floor plans that are going to be very flexible for research purposes. So they also need, and then therefore we have decided to have gravity systems to be a steel gravity system because it was fast to build. It is very efficient when it comes to the long spans. So you have less columns within the actual rooms. Like you have columns here, so like maybe these spans are a little bit different. So And also it has this composite action with the steel, so it was very effective. But the actual story was the lateral system, the system that needed to resist the earthquakes. And we have evaluated the usual suspects, including the concrete shear walls and special moment frames. But in the end, we have decided to go with these unique systems called braced frames, BRBFs, actually brace frames resistance, and they are very unique because they act symmetrically, both tension and compression, because usually concrete acts in compression and we add steel for the actual tension behavior. But because they have this instilled core, sorry about that, because they have this steel core inside of them, then they have this symmetrical action, they have better energy dissipation, better drift control, and it's perfect for this building height, while also having a less braced frames within the final design, which means less architectural impact, and also having less structural cost because of the less detailing. Another project that I worked on in California went through a lot of iterations, and this is not even actually the final design that they had. They had so many iterations. It is located in the UCSB, University of California, Santa Barbara, which is one of the campuses within there. And we have been tasked to design 5 different buildings, 5 to 8 stories each. We have chosen to go with the gravity system that it was like a 2-way post-tension slab with the regular gravity columns, concrete gravity columns, but the lateral system, the one that resisted the seismic ground motion, because we have a lot of seismicity here, we have liquefaction, and the actual geotechnical properties of the site have dictated that and determined to where we're going to use these ductile coupled shear walls. But as I mentioned before, the actual challenge of this whole project was the constant iteration with the architects, with the clients, trying to see where each of these units needed to fit, because this is specifically designed for a campus, for student housing. So every single unit needed to be certain width and length, and we could not change that. So we needed to negotiate where every column goes, where every shear wall goes, what is the thickness, what is the opening, and every single detail. And I have like probably so many iterations on my computer that I have filled the memory of it. So like I needed to call OT to fix all that. But we finally started production on that, and the actual coordination with the architects was very challenging, but I think we managed to get there. And it's also important just to mention this communication between the client needs, the architectural program, and the structural efficiency and the safety for the people that are going to house here, especially the student population. Another interesting project that we recently we submitted permitting, and then we had a call the other day that it was going through next phase, which is very, very cool. It would be my first high-rise actually to work on that I can talk about, but it's located actually in San Francisco. And I was on this team that tried to evaluate what type of structural system is most efficient for this specific high-rise. But the trick is we have one site, but the client doesn't know which of the 2 buildings they're going to do. Do they want to do a mixed-use office towers that is 213 meters tall, or they want to do an office tower that is 230 meters tall? Because they couldn't decide, we had to do both. We had to do analysis and structural analysis for both of these towers and trying to understand which lateral system is the best for this specific structure. And how is it going to interact with the buildings around it? Because we have very unique soil conditions. Are we going to need the piles? Are we going to use a mat foundation? And also, very importantly, the load criteria. We have different loads here, different loads there. Even though they are very similar heights, they are behaving very differently, and they have different kind of response to the seismic ground motion, to the wind criteria, and so on. So we needed to look into those. As I mentioned before, communication with the clients is very interesting, and we needed to kind of coordinate with them, and both structurally and architecturally how this building will look like in the end. But also, it needs to be very pleasing to the eye of the actual public, because it is going to be located in the heart of the San Francisco, and it fits with the environment with the Salesforce towers and some other ones around the region. So designing 2 towers wasn't enough, so they put me on a project now that I'm part of the project engineering group, where we're designing 3 different towers on the same site with a full basement. I don't think basement is shown here, but there's a 6-story basement as well. So we have 3 different buildings. We have the hotel condo, multifamily, and the office building. And even though all 3 have these same structural systems, when we design for the shear ductile coupled shear walls, they are all behaving differently. They have different heights, they have different loading criteria, they have different program or an organization, they have different areas and so on, and also the loads that are associated with them. So how do we do all that? And in addition to all that as well, we have not only internal architects, but we're also working with the outside architects. So that communication is very crucial in how we are going to achieve the best and most efficient structural design. And I think each month we have to actually go to Texas, meet with the clients and with everybody. It's a whole day thing, so it's very interesting to talk to. But the unique thing about this project is it wasn't designed for seismic activity as all the other projects that I talked about. They're specifically seismic governed. But in this case, it's the wind. So we needed to do a lot of wind tunnel testing to get the data and get the shape of these buildings to understand what type of loads are going to be imposed and how we design for those. And thankfully, we have a lot of communication with our other offices in Chicago, in New York and some other ones across US and the world, and they have this knowledge about the wind load criteria and how we design for those, how we most efficiently design for them. And we have implemented that and designed the towers the best way possible, and submittal was 2 days ago, so I had to work until like 4 a.m. in the morning to finish that, and hopefully it's gonna go well. So I think we need to start construction within the next few months or so. But all the things that we do in SOM isn't just about the buildings, so it isn't just about high-rises. One interesting project that have been going on within SOM for past like decade or so is this new type of seismic connection. So typically when we design for a seismic connection, seismic system that is going to resist earthquakes, it is designed to fail. Like it's intentionally designed to fail, to be replaced with a new system and maybe repaired in some sense. But we have tried to, and we have successfully actually did a design of a pin-fused moment frame connection, which dissipates the energy through friction-based system. It's a friction slip mechanism that is housed right within this connection right there. And it takes on the seismic forces. It provides for better energy dissipation, larger drift, and also we don't have this repair that we typically need when it comes to like regular seismic connection, like the shear walls the coupling beams in the shear walls that are designed to fail, or some type of a seismic system that is steel that is going to yield after a seismic activity. So I was brought back to my PhD years. I went to the lab, I had to set up the specimen. I actually had to design it from scratch, order the parts, get the shop drawings, put the data together, which, for example, this is one of the graphs. I know it's complicated, but when we test this specimen, so like we apply the load right here, the actuator load, it goes up and down. And we have the displacement versus force, so we apply the force, and then we have certain displacement, and we go in a different direction, and so on and so forth. And then you see this is the drift values that we need to see. This is the minimum one that we're needed to reach, and we went all the way to 6%, so which means we're very good until we actually reach this yielding point where it breaks. So it was a very interesting thing to do. So, as I mentioned, SOM doesn't just do structural engineering. It doesn't do structural engineering of high rises. It also does a lot of research and innovation. For example, they did this Novus vault in Italy where they use HoloLenses to build structures without actually having the plans on the site. They're working on some energy vault where they're trying to harness the energy and also preserve it within the building. They're using robotic systems to construct different structures or kind of design around them. And we're also, for example, using shape memory alloy to kind of dissipate the seismic energy for the seismic energy in the building that had been just implemented in University of California, Berkeley. So I kind of wanted to tie into that research and see what I can do with it. So whenever I said before that I took a break from that extreme environment research, it wasn't actually true. So I wanted to understand how we do things here on Earth, like how we design things on Earth, and apply my PhD research and all the publications that I've did throughout my grad studies and understand what happens when Earth is no longer the site. How do we design for that? Like, how do we go into that new region? So, because we have unique criteria, we have the different. We have 14 days of the day and 14 days of the night. 14 days of the night. Yes, we have vacuum conditions. We have moonquakes. We have the regolith dust. We have a lot of temperature fluctuations. So all these unique loads that are very different than what we actually design here for Earth. So how do we do that? I have kind of built upon what has been done before. SOM has did this Moon Village project, mostly from the architectural perspective rather than structural engineering. But I wanted to build upon this and see where we can go further. So they have worked with European Space Agency as MIT to see how can we house humans there and how will that master planning look like. So I have built upon that and try to understand what principles of designs do we actually need to leave behind on Earth. So what practices we're used to here, what we need to abandon here, and also maybe develop new ones out there. So when it comes to the actual architecture, we need to understand how do we design for survival, how do we design for comfort and also isolation. We need to understand how structural engineering works there, how we have the new gravities, new loads, and new logic, and also use a robotic construction. We don't have humans anymore on the site, so how do we actually approach that with having built by bots, not by boots? And I have managed to kind of form a team within the company. They were very eager to do this, and we have identified 4 different regions at this point, including the planning, where it was master planning with the Moon Village. We have identified the building systems, where we're trying to understand what building systems can, for example, NASA make or some other space entities can make that we're collaborating with, and what type of structures we can build upon that. Then we are trying to develop new systems, for example, for seismic isolation, because they have moonquakes, which I'm going to talk about just in a minute. And we have the new materials. We're not going to have regular concrete on the moon, so how are we going to build that? We cannot transport material from Earth because it's very heavy, so how do we actually approach that problem? So we were fortunate enough to actually apply for 2 grants within my first year because I understood how the system works within NASA. And we got them both, actually. So the first NASA grant that we got focused on the foundation design and seismic protection of lunar infrastructure utilizing bulk regolith. So basically, we have obtained the data from the Apollo missions that they have gathered for the seismic data. So they have gathered a lot of seismic data. Around 13,000 moonquakes have been recorded. Yes, we have earthquakes and we have moonquakes. This is a typical earthquake recorded in California, Berkeley, for one of the projects that we did. And it is superimposed with a moonquake. So this is a moonquake signal. This signal lasts for 1 minute, 90 seconds or so. This is a moonquake lasting for almost 2 hours. So now just imagine just shaking with a very high frequency for 2 hours. So we're how do we even design for that? Is that designable? So we took the task on. We worked with our consultants for small business, and we worked with university to do this task. And it was very interesting because we have tried to identify different systems. We tried to see how different systems behave under the same ground motions, because different systems have different natural frequencies. So we have evaluated some types of domes. We have used half cylinders, hyperboloid, the tall lunar tower that NASA has produced, and also our prefabricated habitat that we have done through Moon Village project. And we have developed the first response spectrum for the moon, which doesn't exist yet, right? This is the first one. And typically we use response spectrum for design on Earth when we design buildings. But in this case, it was very unique because we don't have enough data, so we needed to do a lot of studies and understand what probability of exceedance we're gonna go for, what is the risk category, and what is the actual period of the structure that we're gonna design for. So for example, if your structure has a period of 1 second, you're going to have much higher acceleration acting on the actual structure. But if your structure has high period, that means you're going to have less acceleration, less impact on the actual structural system. So we actually did 2 studies because the dome has smaller periods, higher frequencies, while the tower has longer periods but higher periods but lower frequency the other way. So firstly, we looked into the tall tower to see how it behaves under this response spectrum, and we have tried to understand what overturning moment is caused by the seismic activity, and what is the restoring force or restoring moment that is pulling the structure back to not actually topple over. And based on some of the studies that we did, it usually topples over because it wasn't designed for actual seismic activity. They haven't even looked into this, so we're trying to teach the NASA, the space community, how do you actually design structures that are that have seismic activity, because they haven't done that before. The other one is the dome that we did, and we designed this one that is placed on the regolith. On the regolith is the lunar soil, and we applied this friction force and the passive pressure force that are resisting this ground motion that is applied onto the structure, and we saw sliding. So we're like, this structure is going to slide. This specific thing you designed, it's sliding due to the seismic activity that we have obtained from the actual Apollo missions. Everybody was ecstatic. Everybody couldn't believe it. So we're publishing a few papers now, and hopefully we're going to get a future proposal about this. Another interesting project that we did, that's the second NASA grant that we worked on. We tried to implement our knowledge from terrestrial engineering, from topology optimization, and actually a couple of projects that we did within SOM across the world, and applied to lunar towers. We tried to see what type of materials can like a certain individual or company produce, and how can we shape the structure around that specific material. For example, on Earth we have concrete, we have steel, that's what we build with. But on the moon, for example, if they use this local material, if they use the site material, we can get this developed like glass ceramic material. Imagine having a tall tower that is built by glass. So how do we even shape that? So we try to utilize our topology optimization and see what is the best way to, where's the best way to place the material within that structure. So we take on the design space, like how wide and big we're gonna have that structure to be, how that material is going to propagate within the design space due to the certain loads, which are definition of the unique lunar loads, and then we kind of shape that structure around those loads and seeing what we can produce with the post-processing. So we have this typical Mitchell truss that we call. There's a lot of studies have been done on it. There's a lot of math and physics to it, but basically we have this typical system that you have 2/3 of the structure is down, 2/3 of the structure is up, and then 1/3 of the structure is down here with these systems. So a very unique opportunity. So we proceeded with this and see where it goes next. Very interesting, another opportunity that we're proceeding right now is with NASA Ames, for example. There's a couple of other ones that I cannot share yet, hopefully soon, but right now we're collaborating with NASA Ames, which is located in the Mountain View, where we are, and they are using they actually developed already these robotic systems. So all of this that you see, I know it's a rendering, but they actually built it. I know there's no pictures of the actual robots, but they actually put these structures together robotically. But none of these are designed by a structural engineer. They're just put together by mechanical engineers or electrical engineers, roboticists. So they haven't designed a structure for seismic activity, for live loads, for any other type of loads like meteorite impacts. So we are stepping in and seeing and telling them this is how we design structures here. So how are we going to design these structures on the moon with the proper design criteria that we have? And we applied for some proposals, and we're waiting on the response right now. Hopefully that goes through. Additional thing we are part of was actually this opportunity started a couple years ago. No, actually like 4 years ago. I am working with this ASCE, American Society of Civil Engineers, the Aerospace Division, for Space Engineering and Construction Committee. So everybody's familiar with building codes. How we design here, how we use those building codes to build something, and the building needs to be up to code, right, to be buildable, to have this like social kind of social status, and that the building is safe to enter. So we're trying to do the same for the moon. So we have defined all the sections, all the chapters, identifying all the loads that we know of, and all the data that we have gathered so far, and estimated this minimum design criteria for certain structure on the moon. For example, if we have dead loads or regolith loads, like we have here on Earth, that are the permanent loads that are located in the structure, we have, for example, the seismic design criteria that I'm leading this part, that how a moonquake will behave and how it's going to impact the structure. We have meteorite impacts, we have thermal loads, rocket craft and landing and launch loads. So all these loads are kind of working together in one synchronous aspect, and they're all combined in the combination of loads, just like we have here on Earth. So we're trying to teach NASA, like, how do you communicate this with the structural engineer, with the architects, to actually build something with gravity. And currently we are kind of part of a lot of conferences and panels, we usually argue a lot with mechanical engineers and electrical engineers. So this is me and my fellow 4 civil engineers that are actually at the conference. And it's very interesting just to kind of hear us argue. We're also working with NASA, with Ames, and now recently with JPL as well, trying to see how we can work together with these people, with the space companies, and also some of the other companies that we work with right now that are specifically in the space sector, and also a lot of universities as well, because people are eager to learn this and to expand this lunar economy. But hopefully, this is not a first time I'm presenting this in Bosnia, and we get some more interest in this very unique topic and application. Iako sam sada sam vam pokazala sve te neke moje korake i od studija do velikih projekata, od tih prvih građevinskih koraka pa do velikih poslova, i mogu samo da kažem da sam nekako shvatila da te granice nisu samo stvar većine objekata ili mjesto tih objekata u svijetu, i da je to samo način razmišljanja. Znači, mi moramo razumjeti kako razmišljamo, kako ćemo dalje ići, kako ćemo otvoriti put za druge, za nas i za naše buduće generacije. I ja se nadam da moje iskustvo i moj put što sam podijelila ovdje može nekome pomoći da stvori novu ideju ili otvori taj neki novi, ili odaberete neki novi izbor koji je novi izbor i izazov koji nekako izgleda predaleko, i ako to se uradi, onda znači da se taj krug baš zatvara. Zato, hvala.
Thank you, Nerma. We have time for one quick question. Do you have any questions? Okay, sure.
Hello? I just have a question because, as we saw, you did a lot of research about the physics and the math required to build objects on the moon. How does that, and can that be translated to building objects on Earth? Is there something that you learned, that you found something specific that you couldn't see in the data from the Earth data, and can it be translated back to the moon?
Yes, of course. And one of the two perfect examples that I can share about are materials and a way of construction. So we're used to concrete, we're used to steel, but what if we can use other type of materials? There are maybe green materials that require less energy to be produced, they require a kind of less manpower, less just kind of energy to make that material, but also has good compression properties, good tensile properties that we can implement it in a structure, which we're trying to do right now with these lunar infrastructure components. So that type of we can learn from innovative materials and how we design around those. Another one is construction methods. We have used to have people on the site, to use cranes, to use all these kind of tools that we have at our disposal, but what if we can even minimize more our human assistance, because we can that way impact the lives better. It's healthier, it's safer for the humans to actually work with the robots rather than tying the rebar together or carrying a heavy load or climbing very high heights. What if we can use drones? Well, we can use some 3D printers to actually design these structures to be printable, to be designable for this specifically robotic construction, but also utilize the human assistance while minimizing their health and safety, or maximizing their health and safety, sorry.
Thank you once again, Ms. Nerma.
Question?
Okay, sure.
Thank you. So my question is, in your work, do you use BIM methodology and tools? And the second part of my question is how realistic in the close future is this all lunar infrastructure, I think?
So I have a slide. I didn't have a slide here, but I have another presentation that I gave about how do we design on Earth and how do we design on the Moon. So we do use a lot of BIM systems on Earth here and kind of understand how the whole structure interacts with each other, with all the components. But we cannot really do that linear process on the moon. So we cannot have, we're going to design this structure, we're going to put this, we're going to build it this way, and it's going to have this specific characteristics for structural engineering. In this case, we need to have a feedback loop. So we need to have a whole loop of like, this is what the structure needs to do, this is how what it needs to look like, this is how robotic construction will happen. But then you also need to adjust that structural innovation and structural design and architecture because of those robotic needs and kind of robotic limitations that we have throughout that design. So everything needs to be interacted, and that BIM modeling is very essential because we want to monitor the structure in real life, like in real life. We wanted to understand how, like we wanted to have the live model of the structure while it's being built to understand how the load propagates, because we don't have humans on site just looking and like, okay, the robot is going to do this. Or we don't have a human tying the rebar on the moon and saying, yeah, this is good, this is up to code. So we're going to have this BIM modeling, BIM approach that monitors the health of the structure before construction to kind of understand what it is, during construction to understand the load path, and after construction to understand how the structure behaves in the environment for like 10, 20, 50 years or so. And what was the second part, sorry?
Like how realistic in the next 10 or 15 years is this, and like has SpaceX contacted you maybe?
SpaceX did contact me, yes, but I did not want to work there yet. So it's very realistic. I think we can engineer everything. Like we have engineered so many things, so many great things around the world, and I think this community is very innovative and everybody's pushing boundaries in their own profession, not just in engineering. So I think it's possible. We have this passion, we have the knowledge, but all we need is vision. All we need is persistence and just to kind of push these boundaries and push it on to the next generation and promote it within the community. Don't let this thing be a sci-fi movie that we watch on a TV, because in the US, this is just a regular talk. Like everything is possible if you just want to kind of go for it and do it. You just need to find a practical way and practical vision of achieving it, but I think this vision is possible. If it was not, I would not be doing it. Yeah, thank you.
Thank you, Nerma.